In this video, I want to do a stoichiometry problem using gas laws. So stoichiometric relationships. Remember, anytime we're doing a stoichiometry problem, that's where we're using the coefficients in our balanced equation to convert from one substance to a different substance in that balanced equation. And I think the easiest way to do this is to just jump into a problem and go through it. So we'll just start with an example. So I'm going to have sodium azide. Remember, azide was one of the polyatomic ions that you needed to remember. It was N3 with a -1 charge. So there's one N3 for every one sodium. And this is actually a solid. And then it's decomposing, so this is a decomposition reaction to produce 2 sodium and a nitrogen molecule, which is gas. So I said 2, but I didn't write it. We have to balance it. So because I have 3 nitrogen on the reactant side and I only have 2 on the product side, I do need a 3 in front of this, a 2 in front of this one, which gives me the 2 sodium, so that's the 2 in front of the sodium solid. So 2 sodium on each side, 6 nitrogen on each side. Again, whenever we're doing stoichiometry, we need those coefficients because we're going to be converting from one substance to another, and the only way to do that is to use that Moldable Ratio, right? The coefficients in my balanced equation. So our problem, how many liters of nitrogen gas at 1.15 atmospheres and 30.0 degrees Celsius are produced by the decomposition of 145.0 grams of sodium azide. So if you didn't have the heading on the top that says stoichiometric relationships, how would you know this is a stoichiometry problem? Because we're given, right, a mass of sodium azide, and we're asked, right, how many liters of nitrogen gas are we making? So again, whenever we're going from one substance to a different substance in our chemical equation, it's a stoichiometry problem. We need to use those coefficients. And then also remember, those coefficients represent the number of moles of our substance, not the volume or the number of grams. So I do need to get things in terms of moles. So kind of the plan is I'm going to convert grams of sodium azide to moles of sodium azide. Once I do that, I can use the coefficients in my balanced equation, right, this 2:3 ratio, to figure out how many moles of nitrogen I have. Once I do that, we can plug it into our ideal gas law and figure out how many liters, right? I have a pressure that's given to me in the problem. I have a temperature. We're solving for liters, and we can get moles using the stoichiometry of our equation. So first step, we need to know the number of moles of nitrogen because we want volume of nitrogen, right? We don't want volume of sodium azide. We want volume of nitrogen. We're given mass of sodium azide. So to get from one substance to another, we need to do that mole to mole ratio. So first step, I have 145.0 grams of sodium azide. We do need the molar mass of sodium azide because we need to convert it to moles. So I'm going to grab my periodic table and my calculator here. So 23.00 plus nitrogen, which is 14.01, and we do need to multiply that by 3 because there's 3 of them. And I get my molar mass to be 65.03 grams per mole. Because grams are on the top, I am going to divide by that molar mass. So my grams cancel. So I now have moles of sodium azide. This is where we're going to use our coefficients. So we're going to use our Moldable Ratio. I know for every 2 moles, right, again, and this is just coming from my coefficient, for every 2 moles, I forgot the word mole, for every 2 moles of sodium azide, we're going to produce 3 moles of nitrogen. And again, those numbers are just coming right from here. So my moles of sodium azide go away, we're left with moles of nitrogen. Once I get that number, then again, we can plug that into our ideal gas law to solve for liters of nitrogen. Right, if we wanted liters of sodium azide, which wouldn't make a lot of sense because it's solid, but if we wanted liters of it, we wouldn't have to go through this step. The clue, 2 different substances. So 145 divided by 65.03, multiplied by 3, and then divided by 2. I'm going to do that again. I hit something wrong on my calculator. I got a really big number. That's how you know that you goofed up, because it makes no sense. Always think about your answers so you can try to catch mistakes. So I got 3.34 moles of nitrogen. Of course, our question wants volume, so now we can use our ideal gas law to convert. So PV equals nRT. Pressure is given to me in the problem. Right up here, 1.15 atmospheres. If it wasn't in atmospheres, we would have to convert it, just a straight unit conversion, and I would give you those conversion factors again. I don't expect you to remember how many torr or millimeters of mercury or psi there are in an atmosphere. So if you need to convert, I will give you the conversion. Volume is our unknown, that's what we're solving for, and we just determined using stoichiometry to be 3.34 moles. R again is our constant, just grab that from your periodic table. Make sure you use the right one, not the one that has units of energy in it. And then temperature is also given to us in the problem, 30 degrees Celsius. Remember, our temperatures do need to be in Kelvin, so I am going to add 273 to that to get 303 Kelvin. Once I have those numbers, we'll just plug it into our equation. So 1.15 atmospheres multiplied by volume, which is my unknown, 3.34 moles, my constant, multiplied by my temperature. And then we want to solve for V. So I'm typing into my calculator right now. And I got 72.4 liters, actually 0.2 liters, right, of nitrogen gas. So let's do one more stoichiometry problem for us. So example, and this time I'm gonna have 4 iron, which is solid. And this one's reacting with oxygen, sorry, not an arrow. So reacting with oxygen. And we're producing iron 3 oxide, which is solid. And I did just balance it for us, so 4 iron for every 3 oxygen, producing 2 iron 3 oxide. And our question, if 1.45 liters of oxygen is reacted at STP, how many grams of iron 3 oxide are formed? So again, we know this is a stoichiometry problem because we're given information about oxygen, we're asked information about iron 3 oxide. So again, we're going from one substance to another substance in our balanced chemical equation, so we're going to need the coefficients to convert between them. And then again, remember those coefficients represent the number of moles of the substance, so we need to convert liters of oxygen to moles of oxygen. The way we're going to do that is we're going to use our ideal gas law. So liters is part of it, so is moles. I do have a temperature and pressure because I'm at standard conditions. Once I solve for moles of oxygen, I can then convert it to moles of iron 3 oxide using my coefficients, and then for moles to grams using my molar mass. So this one time, we're going to use the ideal gas law first. So P, I'm at standard pressure, so 1 atmosphere. V is given to us as 1.45 liters. N is my unknown, that's what we're solving for. R is my gas constant. It's on your table. By the time you do all the practice problems though, you'll probably have it memorized anyway. And then T is my temperature. Again, I'm at standard state conditions, so 273 Kelvin, or 0 degrees Celsius, but again, everything needs to be in Kelvin for these problems. My other units are okay. So my pressure is in atmospheres, my volume is in liters. If they weren't in those units, make sure you convert. Some of those conversions are on your table. They will be provided. You don't have to memorize for pressure. If the volume was in milliliters or some other metric system unit, though, you do need to know those conversions, right? They're the ones that you needed to learn at the very beginning of the semester when we went through the metric system. So plugging everything in, my pressure, right? I'm just plugging it into my ideal gas law here. So pressure multiplied by my volume is equal to my number of moles, which is my unknown, multiplied by my constants, multiplied by my temperature. And then a little bit of math here to solve for my number of moles. I'm going to grab my calculator. And I end up with 0.0647 moles of oxygen. So now that I have moles of oxygen, we can then use our coefficients, right? For every 3 moles of oxygen, I'm going to produce 2 moles of iron 3 oxide. Once I get moles of iron 3 oxide, we can convert to grams using our molar mass, right? Every time we go between grams and moles and grams, always molar mass. So 0.0647 moles of O2. Our coefficients were 3 moles of oxygen, and again that needs to go on the bottom so I can cancel moles of oxygen for every 2 moles of iron 3 oxide. And then I do need the molar mass of that, so I'm going to grab my periodic table and my calculator. So 55.85. There's 2 of those, so I'm going to multiply by 2, and then 3 oxygens. So I get my molar mass to come out to be 159.70 grams per mole. And I know to multiply by my molar mass, right, because I need moles on the bottom so that they cancel. And then, again, just a little bit of math. And I ended up with 6.89 grams of iron 3 oxide.